Hello, game theorists. So we're getting started here in Chapter 2. In case you're wondering what happened to Chapter 1, well, Chapter 1 is a very basic introduction, not a whole lot of substance there, so I'm skipping ahead to Chapter 2. So Chapter 2 have this section on 6 considerations for thinking about games. So this can help frame your thinking when you're studying game theory. Consideration number 1. Is it a sequential game or is it a simultaneous move game? That refers to how the turns are played out. So if it's a sequential game, the players take turns. Like maybe you make the first move and then I make the second move, etc. So games like chess are sequential. Tic-tac-toe is also sequential. Now, a simultaneous move game means the players move at the same time, or more precisely, the players move without knowing what their opponent is doing. So games like rock, paper, scissors are simultaneous move games. So why I said it's more precise to say move without knowing your opponent's move. Well, a game like rock, paper, scissors can be played with turns in a way that's equivalent to the more traditional version. So traditionally, you pick either rock, paper, or scissors at the same time your opponent does. Here's the way it's going to work out in the exact same method. Maybe I move first, picking rock, paper, or scissors. Maybe I write my move down somewhere on a piece of paper and stick that in a sealed envelope. You then make your turn, picking rock, paper, or scissors without knowing what I wrote down in that envelope. It's equivalent. Either way, you're moving without knowing what I just did. So it looks like you're taking turns in that I moved first and then you did. However, it's the same as the usual version because in both cases, neither one of us know what our opponent's doing. So that's why I say more precisely, a simultaneous move game means that you move without knowing what your opponent just did. It doesn't actually have to be moving at the exact same time. You can move at different times as long as you don't know what your opponent is doing. So this affects the analysis. Now, if you were to play rock, paper, scissors in a sequential fashion, where you take turns and you also know what your opponent did, that's going to change the game quite a bit. If you move at the same time and you're playing rock, paper, scissors, you have even chances. But if your opponent moves first, they got to pick, let's say they pick rock, and you know that, you just picked rock in their previous turn, then you can always win by picking paper. So sequential move, rock, paper, scissors, is going to affect the game because now you have more information because you know what your opponent did on their previous turn. So that's why it matters if a game is sequential or if it is simultaneous. So we'll develop some separate tools for looking at each of these two kinds of games, and then later on, I believe it's in Chapter 6, if I'm recalling properly, later on we'll reconcile and find a common framework that works for all kinds of games. So, first consideration, do the players take turns or do they not take turns? Now let's move on to consideration number 2. Is it a zero-sum game? So in a zero-sum game, one player's gain is another player's loss. So games like poker are zero-sum. In order for one player to win at poker, everybody else has to lose. Chess is also a zero-sum game. You can't have two winners in a chess game. Either someone wins or someone loses, or it's a draw. You don't have two winners. So, not all games are zero-sum. A lot of board games or card games are zero-sum when there's only one winner at most, or it could be a tie, but you never have multiple winners. Now, not all games that we study are zero-sum. One big application of game theory is looking at firms in competition. It's quite possible that in a competitive environment, all the firms make a profit. So you could have all the firms be winners in a marketplace. So not every game is zero-sum. Now, why it's relevant if a game is zero-sum or not, it's because it affects the player's willingness to cooperate. So in a game like poker, the players are probably not going to cooperate at all. If I help somebody else, I'm just helping them beat me. I can't win at the same time as they win. So games like poker, probably little or no cooperation. Now, if firms can compete, and that's a non-zero-sum game where all firms can be profitable, then you do have to worry about firms colluding on price or cooperating, charging a higher price that's closer to the monopoly outcome. So, to clarify, cooperation sounds like a good word, but in the context of firms and competition, it's actually not a good thing. So, think about cooperation more neutrally. It's not always good or always bad. It's going to depend upon the context. One thing you can safely say, though, is that in a zero-sum game, you'll probably see less cooperation than in other kinds of games. So knowing whether a game is zero-sum can shape your strategy in determining, do I want to reach out to other players and try to work together with them, or do I just have to go at this alone? So you want to be aware of that when you're making those decisions. Consideration number 3 is closely related, though it might not appear to be so on the surface. So consideration number 3 asks, is the game played once or is the game repeated? So what does that have to do with cooperation? Well, if the game is played multiple times, it's possible that I could try to punish someone who's uncooperative. So you make some deal to cooperate in round 1, but you defect, you don't go along with the deal, then I could try to punish you in round 2 by being uncooperative. Similarly, if you cooperate in round 1 like I want you to, then I could reward you by cooperating in round 2. So repetition can create some incentives for cooperation. we'll see several examples in that. We'll actually have a whole chapter dedicated to repeated games, and we'll see how that works. All right, our fourth factor is about information. So we'll study several cases in this course. So one of which is perfect information. So that means there's no uncertainty about any external circumstances or about the opponent's situation. We'll make the definition more precise when we look at sequential games. So one example of a game with perfect information is chess. So if you're wondering why I keep bringing chess up, I'm a chess player. I go to tournaments. I used to go to tournaments pre-COVID before it all got canceled. So whenever chess is appropriate as an example, I'll probably bring it up. So in chess, you know all the previous moves. There's no uncertainty about where any of the pieces are. And I know external events that will affect the game. So that's a pretty clear-cut case of perfect information. If you don't have that, then that's what we call imperfect information. So on chess, I know all my opponent's previous moves. If I'm playing rock, paper, scissors, I don't know what my opponent's going to play, and that's going to be creating imperfect information. We'll get a more precise definition later. Now, when information is imperfect, there can also be a possible case of asymmetric information. So, in rock, paper, scissors, information is imperfect, but is symmetric. I don't know what you're going to play, but also you don't know what I'm going to play. Well, not all games of imperfect information are like that. Sometimes in the game, one player is going to be more informed than the other player. So one example that's often used for asymmetric information is buying a used car. So when you sign up for a class in game theory, you probably weren't thinking we'll be talking about used car sales, but game theory is about much more than board games. It's about this framework that can be applied to many, many, many situations, one of which is buying a used car. So the seller of the car knows if it's good quality or not. They've driven it for probably years and years, and have a pretty good feel for what its strengths and weaknesses are. If you're the buyer and you're not some car expert, then you have substantial uncertainty about the car's true value. So in that game, where selling a used car, the seller is going to be more informed than the buyer. And that's going to have some implications for the market. We'll talk about examples like that in future chapters. So we're just laying a lot of foundations today, not going terribly in depth, but you'll see a lot more of the stuff in the rest of the course. All right, that wraps up consideration number 4. Let's look at our 5th consideration. It's about the rules of the game. So the rules just etched in stone, or can they be changed, manipulated? So, to be clear, most of the time we'll look at games where the rules are fixed. They're a lot easier to analyze. However, manipulation of the rules can be very, very important in playing a game in real life. And we'll have a chapter dedicated to that consideration. It's hard to model because there are so many different ways you could change the rules. There are just kind of limitless possibilities there, but it does have to be taken into consideration. So we'll go back to the example of firms in competition. So the government sets the rules for the marketplace. They have regulations and all that kind of stuff. However, governments can be lobbied or, in some cases, bribed into changing the rules. So it's not just about playing the game as it is currently set up. It's also about, can you transform the game into something more favorable by influencing the government or the referee? Oh, for my notation, I should have said this. By X, I mean example. I've been using that, I guess, throughout this video, and hopefully you guys got it, but in case you didn't, there is the definition. So, like I was saying earlier, firms in competition is often modeled with game theory. You saw it back in principles and probably also in intermediate micro. So we use game theory to model those situations. All right, that's our 5th consideration. Now for our very last one, number 6. So if players make an agreement between themselves, are those agreements enforceable or not? So games that have enforceable agreements, we call those cooperative games, or also called, some terminology, coalitional games. So usually the way the games are set up, when agreements are enforceable, there has to be some benefit to working together. If there is no benefit to working together, then there's no point in having an agreement in the first place, so that's the only interesting case. The question then becomes, how do you divide up this surplus, this extra benefit you get from cooperating? What's a fair way to do that that everyone can agree with? There's a whole separate branch of game theory that's dedicated to that. Now, we'll look at here in this class is mostly about unenforceable agreements. We call those non-cooperative games. That's going to be the focus of the vast majority of this class. So one big economic example of game theory is, we said, firms in competition. Laws do bar firms from colluding, so they can't make agreements with each other, and if they could not enforce them because they're illegal. So we'll focus a lot on non-cooperative games here. So those are the 6 considerations for thinking about games. Be sure to tune in for our next episode, in which we'll look at elements of games.